Our next presentation is everything you need to know about Raman Optical Amplification. Mike Harrop of Application Engineer and CTO Office of EXFO. I'm just going to bring that up a little bit. Mike is a chartered engineer with over 20 years of experience within the field of fiber optic test and measurement. Mike's previous roles have included Principal Research Engineer at BICC Cables, Corning Cable Systems, included supporting internal and external projects all over Europe and the Middle East. Mike now shares his time between EXFO's application engineering group for their optical physical layer product lines and the CTO office. This experience means that Mike has developed a great deal of knowledge in the aspects of optical fiber networks, including design, manufacture, installation, and commissioning. Very busy. During the time with BICC and Corning, he headed up the test and measurement group, starting with providing optical, mechanical, environmental testing for the companies, including manufacturing units. Mike was then responsible for establishing the company's European Network Characterization Service. Core competencies here included advanced OTDR, IML testing, as well as a deep understanding of dispersion, CD and MPD, and DWDM transmission issues. Mike has a BS Hons in Applied Physics with a measurement and instrumentation from Manchester Metropolitan University. He was presented at ECOC with, he has presented at ECOC with materials for EXFO's Wave Review and is a member of the ITU Study Group 15, BSI Standards GEL 86, and a member of the Deployment and Operation Committee within the FTTH Council. Mike, over to you. Thank you.
Oh, good morning, everybody. As that long bio told you, my name is Mike Harrop. I work for EXFO, test and measurement designer and builder. Today, we'll be talking about Raman Amplification. I mean, part of my role, as mentioned, is application engineering, so pre-sales, supporting our customers in Europe, Middle East, and Africa. And a portion of my time is with the CTO's office, where again, we're working with our customers, but we're looking a bit at the future. What are they doing? How are they doing it? And really sort of trying to optimize from a test and measurement point of view, the best way to be doing it. And so this morning, we were talking about Raman. So as a rough agenda, Raman Amplification, what it is, why is it becoming important now? And then after that, look at some of the design considerations that we've discovered or seen that you need to really focus on when you're implementing these in your network to ensure you get the best from this new component. So with the, where are we going to start? So with the technologies that we're seeing today, with the fiber capacity, we've seen very quickly go from 10 gig, 40 gig, to 100 gig per channel on a fiber. And, that's each fiber can support, we're talking maybe 80 channels of 100 gig. But still we're seeing more and more capacity demand. So how are we going to do this, and how is sort of Raman going to help us do this? So the ways that we can do this are several-fold. We can, most systems now work in the C-band, so 1530 to 1565 nanometers. We can extend into the L-band, so go from 1565 to 1625. Obviously, that means more wavelengths available, but the amplifiers that we've got at the moment are usually C-band limited. We can get L-band amplifiers, but that's a separate component. The ROADMs that we use in the network, we need to be separate. And also the L-band amplifiers aren't as good. They don't provide as much gain as well. So there's a performance consideration we need to do there as well. Another way to achieve this bandwidth growth is increase symbol bit. So most, let's say, transmitters now are working in the 30 gigabaud range. What we're going to see over probably the next couple of years is then move to maybe 40 or 45 gigabaud to get more bits in. Obviously, this is going to drive the need for faster electronics. And then another way is that we're going to increase spectral efficiency. I mentioned we can have 80 channels of 100 gigabits on a 50 gigahertz grid, and that's going to fill up our C-band. So to improve the spectral efficiency, what we can do is we can start to push those channels closer and closer. So using a technology, which I'm not going to cover today, called FlexGrid, we can push those down to maybe 37.5 gigahertz. So I can get channels much closer together to increase my spectral efficiency. The problem is when we do that, obviously the channels are getting closer, we start to get things like crosstalk or other nonlinear impairments. So there is a design consideration and maybe a penalty of doing that. And then lastly is the higher order modulation schemes. You know, at the moment, most networks are now being designed for 100 gig, and most of them are using dual polarization quadrature phase shift keying as a modulation scheme. What to do go higher, we're thinking of doing your 8 QAM or even 16 QAM. But to do those, because we've got more bits per board and the constellation diagrams becomes much busier, the amount of noise we can stand goes down. So all these things are going to require eventually some sort of higher OSNR in the system. So before we jump into Raman, I thought it was worth just having a slide, for those who may be not too familiar, on what is the current amplifier technology that we use in the field today. And this is the EDFA, the erbium-doped fibre amplifier. It's a very simple schematic we've got here, where we've got a pump laser pumping into a small chunk of silica fibre that's been doped with erbium. And so we have the traffic coming in from left to right, and it arrives into the EDFA. With the EDFA, a rough sort of overview of what happens is we pump with a very high power laser, and it raises the erbium atoms into a high energy state. And depending on which laser we use, whether it's the 980 or the 1480, it pumps them into different states. But what we want to do is we want to get them into this state here, which is sort of semi-stable. What happens is when the molecule relaxes, it releases a photon in the C-band range. And if just left to its own devices, it will slowly decay. As we pump up, they slowly decay. What is great is that if a signal in the C-band range comes through that erbium fibre, it stimulates emission. So a signal coming in is amplified going out. That's it. And if we just look at the spectrum that we get here, we've got optical power against wavelength. We can see we have the pump wavelength here, 1480, and the resultant amplification window is around here, sort of what we call the C-band. So this is the ASC noise. This is the noise from the random decays here, and then when we put a signal in, it gets boosted. And so we can have 40 or 80 channels in that region, all being optical amplified. So, again, a little simple network here. We have an EDFA here. It's boosted all the signals, and then it's launched into the fibre. As it goes through the fibre, it's being attenuated by the glass properties of the fibre, and eventually there'll come a point where, after a certain distance or a certain loss, the receiver or the next EDFA can't pick it up. So eventually we can only go so far with one EDFA. In a network, when we're designing networks, we want to sort of take our information from A to B, and what we'll do is we'll amplify it at certain points in the network. So in this simple network here, we've got a portion of fibre followed by an EDFA, another network span, probably 60 or 80 kilometers, another amplifier, and so on as we go through the network. The typical span here is 23 dBs of loss, and the amplifiers are set up to compensate for that same loss. So if we look what's happening with the power, we can see that the signal power is attenuated here as it comes through the fibre, and then it's boosted at the amplifier, attenuates as it goes through the next fibre, and so on. So, and at the end here, we can then obviously take that light into the receiver, get the signal. With the EDFAs, as we saw from that quite a broad spectrum, is when we start the network, there was little or no noise in my network. But every time we amplify it, we chuck in a whole load more noise. And then what happens is that noise is attenuated as well as it goes through the fibre. But then when we get to the next EDFA, it adds some noise and amplifies the noise. So you can see that as we go through the network, we're slowly increasing the noise. So my optical signal noise ratio reduces over the number of spans that we do. And the graph here, you can sort of see that we start with a very high OSNR, and we slowly go down. And there'll come a point for different systems, there is a minimum OSNR. At the moment, 100 gig with its digital signal processing is very, very robust. And to be honest, its OSNR is around about 12 dBs. So you can see that for 100 gig, we can go quite a long way. But obviously, they're already talking about 200 gig, even 400 gig. And to achieve those, we've moved from just quadrature phase shift keying to the QAM, so quadrature amplitude modulations. And for those, we need a much higher OSNR at the receiver. So you can see that as we go to 200 gig, we now suddenly become quite distance limited. So this is where the Raman technology is going to come in and really help us here. I mean, Raman scattering was first discovered in about 1928, and actually Raman amplifiers have been around for about 14, 15 years, so they've been around for quite a long time. But it's only just in the past couple of years that we're starting to see network implementations where people are using them in anger. So this time, simple schematic. Again, we have a pump laser, but this time we're not pumping a discrete portion of erbium doped fiber. We're actually counter-propagating up the transmission fiber and using the transmission fiber as the gain medium. Similar to before, so this time also we're pumping 1480 in this case, again to a semi-stable state, and when the molecule relaxes, it releases some vibrational energy and a photon. And because we've lost some of that energy to vibrational energy, the photon is a different wavelength because it has a different energy. And what actually happens is we get a shift. Because it's a lower energy, it's a higher wavelength. So we pump here, and we get a 100 nanometer shift in the gain. As you can see, it's quite narrow spectrally. So what we do is to achieve amplification over a whole band, I think you probably can guess, is that we use multiple pumps, starting around 1430, 1450, 70, 80, to give us a relatively flat gain profile that we can then use with the amplifiers. So now back to the simple schematic we had before. We've added in our Raman here at the very end. It's counter-propagating through the fiber. So the light now is being attenuated, and they'll come to a point approximately 20 kilometers from the end where it'll start to receive the effect from the Raman pump, and will start to receive amplification. And the closer it gets to the Raman pump, the more amplification it gets. So what's happening to the signal power is that it comes to a point where it'll minimum, and it'll start to go up. So what that does is it means we can get to the next EDFA or the receiver with more signal power and therefore a better OSNR. So instantly what that allows us to do is we can go further, or if we're using the higher order modulation schemes, such as QAM, I've got a better OSNR, so I can do more capacity. Also, I can even use this with existing technologies to improve my margin. There may be parts of your network where you're really having to push the current EDFA technology to its limits, and there is very little margin. Adding in a Raman amplifier can keep that margin for if the network ages, or if components change, or you have to do repair, and the attenuation of the link changes. So the Raman is complementing the EDFA very well. So just to compare the two, so with the EDFA, it's the erbium doped fiber that we have in the amplifier that gives us our gain profile. But in the Raman, because we're using the transmission fiber as the gain medium, it's actually the pump lasers that we use to give us the gain profile. So we can use different wavelengths to give us gain in different windows. So EDFA has a higher noise figure, but it also gives high gain. And to be honest, for the last 20 years, it's been the go-to amplifier for transmission systems. From electrical power and gain that you can achieve, it is the go-to amplifier. Raman, you get less gain, but you get less noise. So what is great is that when you use them together, the Raman really complements the EDFA. So if we look at my little system now, where previously we had we were limited to maybe 6 spans. When we start to add in some Raman amplifiers, which are counter-propagating, and we split the gain between the two, we'll give 15 dB gain to the Raman and use the EDFAs to give 8. So we're still getting 23 dB of gain per span. Now, the OSNR limit means that we've now really extended the reach of the 200 gig. So whether it's 200 gig or 400 gig, it's going to be the same. So what this does is it means for the higher order modulations, the NEC technologies, we can use the Raman and still use the same fibre. We've still got the same points where the network and the points of presence were, so they're very hard to shift. So we can now use those, but it also means that we can use, hopefully, existing infrastructure. And also, again, where we've got existing things, we can increase the margin of existing 100 gig systems as well. Okay. So that was just a quick overview of the EDFA technology we currently use and the Raman technology that we're now beginning to see implemented. When it comes to implementing these in the network, well, what have we seen? What are some of the challenges and considerations we need to make? So we saw one picture of a gain curve before. This is just a plot showing the gain curve for different fibre types. There are a variety of fibre types that we can get in the networks, from a G65 to single mode product, dispersion shifted product, which we don't see too much in the UK, but also the G655 products, which are the non-zero dispersion shifted fibres. So depending on the fibre type you have, you can get quite different performance from your Raman amplification. And what is the driver or the gain depends on is the pump power density. And that's directly related to the effective area of the fibre. So the different fibre types have different effective area. So what we want to do here is we want to ensure that when we're doing the design, is that we are putting the appropriate Raman with the appropriate pumps to match the fibre type. It sounds quite simple, but what we've seen is we've had a system design, we've turned it all on, and there's nothing happened because the Raman is for another fibre type. And you think it's quite easy that we all know our fibre types, but the way networks have developed over the years, we've had networks built, sold, chunks sold off, we've had mergers. When the record keeping is very, very good, no problem. But unfortunately, we've seen plenty of occasions when the record keeping is not as good as it could be. And so people don't know the exact fibre type that they have. They might, it's single mode, definitely, but which one? So finding out your fibre type can be quite tricky. So you can't go into the field and take your fibre out and measure the effective area. That's very difficult to do. But what you can do is, if you measure the chromatic dispersion and the properties associated with that, such as the CD in the C-band, the slope, and the lambda zero, you can use that to accurately identify the fibre type that you have. So in this case, on this little table here, sorry about that, we've got standard single mode fibre, lambda zero, down in the O band around 1300. Dispersion 1550 is around 16 to 18 picoseconds per nanometer with a very specific slope. That's easy to identify. Then we've got dispersion shifted fibre, which is the third one down. Zero dispersion, hence the name, in the 1550 window. Okay, but then when we get to the other fibre types, the leaf, the terralite, all the true wave reach, they often have quite similar lambda zeros. So there we have to use things like the dispersion 1550 and the slope to accurately identify which fibre type it is. So when we can do that, we can then ensure that the Raman pump is set to the right level. Of course, there are the situations where sometimes we've got 2 bits of network, sometimes a single mode fibre with a non-zero dispersion shifted fibre. It's quite rare, but sometimes it happens. So there, when we measure the dispersion, we're going to get some strange results. That requires a little bit more in-depth look at the network, maybe using an OTDR to see which sections have been spliced together to work out where the CD is or which fibre type we have. So we've worked out which fibre type it is. Great, we can set the Raman up. So the next thing is, my pump wavelength, as I mentioned, is 100 nanometers lower than my transmission wavelength. If I look at a spectral attenuation plot of a fibre type, or a single mode fibre, if I look at an older G652.A, maybe .B, we could have quite a large water peak. So this is where what could we call it, the water peak? It's where the light around 1383 is absorbed by hydroxyl ions in the glass. And then as fibre has developed, we've had low water peak fibres, and then we've had 0 water peak fibres. And so you can see that our loss per wavelength, as we go through the fibre types, gets less and less and less. Obviously, you can imagine that if I'm pumping at 1430, and I've got a lot of attenuation there, that's just using up my energy for no good. So being able to work out the fibre type and then the loss at that wavelength is going to all go into the system design. So easiest way to measure 1430 is to use an OTDR. Yeah, sorry. Is it OTDR, which I'll come to in a second. To show how much it impacts it is, the graph we got here is Raman gain reduction with connector loss. So this is the connector close to the Raman. But then the influence of the attenuation of the fibre. So 0.24 dB per kilometre fibre will be the 0 water peak fibre, and then we've got successively worse attenuation. So basically a 1 dB connection, and the 0.24 dB, sorry, is the reference 0. And so by having the additional attenuation of the fibre of just 0.09 dBs per kilometre, it's robbing me of 4 dBs of Raman gain. So that can be the difference between the system working and not working. So knowing the attenuation at 1430, it is important. So as mentioned, using an OTDR will allow us to do this very easily. What we're doing here with the OTDR is actually measuring from the Raman end, so the far end of the cable back towards. So you can say that this is the direction of the pump laser, this is the direction of the signal. And the reason we want to do this is because we want to characterize where the Raman is having its maximum gain. That's the last 20 kilometers. And the reason we're starting at that end is that as well as measuring the loss, and you can see that the loss changes as you go down the fibre. Different sections have different loss at that wavelength because of different fibres being used. But also, we want to check, and we'll come on to this in a minute, is what's happening here at the beginning. Connectors, splices close to the Raman are also going to cause an issue. So by starting with the OTDR there, we can use a shorter pulse width and characterize the events in the exchange and close to the Raman. So that was about the gain. So next one is about keeping it clean. So you can imagine this is about the connectors. In the exchange, I'm going to have my equipment, and very often you have a number of racks, ODFs, of your equipment being connected in. So what we're looking at here is the impact of having a connector close to the Raman amplifier. And in lots of places we have lots of connectors, and in some exchanges we can sometimes have 5 or 6 connectors before we even get out of the building. And the impact of these on the performance could be enormous. So what we're showing here is that we've got connection loss and their impact on the gain reduction. So a 1 dB connector is going to give us about 4 dBs. A 2 dB connector, so remember this one, 2 dBs is about 7 dB loss. So it almost comes to the point of not worth having it. And so I mentioned you can have them from the connections in the rack. But obviously, you've got potential of dirty connectors, a single dirty connector, old connectors, because obviously usually we're trying to upgrade existing infrastructure. Or if you had some poor fiber management, such as bends in the racks, then that's going to cause you a problem as well. So it's not just a case of the size of this event, but also the location of this event. If I've got a connector very close to the Raman, as opposed to one maybe 30, 5, 10, 20 kilometers away, the impact on the system is actually very different. So what we're showing here is the same graph, but now at different distances. So the 0 kilometer one is the same one we had before, 1 dB, about 4 dBs of loss. But if we move that connector further away, the impact gets less and less and less until we get to about 20 kilometers, where almost we're out of the Raman amplification window and the connector has no more effect than just the loss of the connector. That's because the Raman gain is being achieved. But a connector early on can be a real pain. Okay. So we often get the question, well, can't we just do more power to overcome these bulk losses that we see earlier in the network? We can, but the problem we see there is that where you have maybe a bad connector or a dirty connector, the powers that we use for the Raman lasers are such that any grease from fingers or any gel from the cables, it just burns. It just burns, that connector will go black, no light of any kind will transmit through it. And what happens is, it's usually discovered during the turn-up phase. The system doesn't come up. And then what happens is people have to go out, find it, replace it, sometimes replace the Raman amplifier. And what that causes is a delay in getting the system turned up. So you can't just turn up and give more power to blast through. So we've talked about the loss of the fiber, the loss of the connectors, the position of the connectors. There's one other problem that we have from connectors, and that's the reflection from them. So the loss is going to reduce my Raman gain. But if I've got a connection with quite a bad reflection, then that's going to cause some problem as well. So what happens is, if I have a connector, some of that light, the light hits it, and some of it is then reflected back. With an EDFA, we've lost that light, but when it hits the EDFA almost acts as an attenuator for that light going the other way. Because we're using the transmission fiber as the gain medium, that reflected light is now passing through the gain medium with the Raman amplifier and gets amplified. And then the worst case scenario is that we hit another connector in the network, and then that reflects back. And that's going back through the gain medium, and it gets amplified again. So what happens is we can end up with a double double reflected signal that's co-propagating with our signal now, and what we call is multipath interference. And this just acts as direct noise on our signal at the receiver. And you can get this from a variety of sources. We can get this from just connector to connector. We can get this from connector, which is then actually Rayleigh backscattered by the fiber itself, the natural property of the glass, Rayleigh backscatter. So even that backscatter can be amplified. And then the last one is just double Rayleigh backscatter, which is low enough that it doesn't cause us an issue. But anything with a connector can really cause us an issue. And just to show this, we're using the amplifier noise figure as a signal, an indication of the quality of the signal. And the main noise figure is determined by the ASC of the amplifier. And then what we have is the equivalent noise figure. And what we've done is we've included the impact of the Rayleigh backs, the contribution of the double back reflections. So our baseline of just the noise figure of the amplifier is the blue line here. And then what we've done is they've done the measurements on the system calculations with increasingly worse connector reflectance. So at a neg 45 dB connector, so this is probably a good quality UPC, so a flat connector in your network. So even that is giving some impairment. But as we go increasingly worse to a neg 21 dB, which is a pretty bad connector, then that is going to cause a 3 dB noise, extra noise on the system. So that's going to directly, again, affect the performance of the amplifier. So, well, again, easiest way to find these, well, if it's an installed link, then using an OTDR. This is actually now, this is the OTDR graph. This is a repeat of the first measurement we saw, but with a much shorter pulse width, so we get very good resolution. Where in the first one we couldn't really see much. Now we can see that in the first maybe 200, 300 meters, we've got two connectors. Reflectance-wise, not very good. So that's one penalty on the noise figure. But also, the loss here, each one is about dB. So that's 2 dBs of loss there. If you remember the graph, that's 7 dBs. So unsurprisingly, this was one that we did in the field. This Raman system didn't come up. Because of the connectors here, and because we had a reflection, because we have a connection here at the ODF, we had a connection here, so we had the multipath interference as well. It was like a perfect storm. So when we're upgrading an existing link, they're using an OTDR to characterize the link, find any bad connectors. For any equipment that's been installed, then cleaning and inspection is the only way to ensure that you don't have any sort of grease or dirt on. Because with the Ramans, it will burn anything there. So we can see here, here's a snapshot of a connector end face. So this is the ceramic ferrule, and then this is the 125 micron core, and then what we've got here is that's in the center, sorry, 125 micron cladding, sorry, and then we have the small 9 micron core. And what we're looking here is for any sort of impairments, particularly around the core, because that will stop it seconds after you turn it on. Okay. So, in conclusion, we have EDFAs since about 1996. You know, they've transformed the world of optical technology. You know, we've gone from 16 channels of 2.5 gigabits to 80 channels of 100 gigabits in the last 20 years, and the EDFA has been the amplifier or the amplifier go-to choice because of its gain and what it's been able to do. But with the higher demands that we're seeing, the longer reach that we're seeing, the higher order modulation schemes that we need to use to get 200 gig and 400 gigs, then the importance or the relevance of the Raman amplifier is increasing all the time. And the way it complements the EDFAs is going to allow us the next generation of technologies, the 200s, the 400 gigabits, the 1 terabit super channels. But when we're doing this, there are some quite basic characterization things that we need to be doing. First of all, fiber type. Do I know the fiber type that I'm working with? Single mode, G652, G655, anything else? What is the fiber manufacturer? Then also being able to check, what is the attenuation in the pump zone? A much older fiber is probably going to have a much higher attenuation at 1430. At 1550, where your channels are, it looks okay. But at 1430, because of the water peak, you may not get the resultant gain from your Raman. So knowing the attenuation there is important and needs to go in the design rules. Then lastly, connectors. The loss of the connectors, the reflectance of the connectors, where these connectors are in relation to where your Raman is critical. And I missed it on the last slide, is that we see in a number of installations now that to try and avoid this last one, they just say, right, what we'll do is, if this is where the Raman will be located, we want you to remove all the connectors. And so they'll go from rack to rack to rack, and rather having a patch cord, they will then do hard splicing to remove as many of these connectors as they can to reduce this impact. So, but if you do these, then the Raman is going to work, and the performance you get will take you on to the next generation of networks. Thank you.
Mike, fascinating subject of Raman Amplification. I have a question from Mr. Callis at the back. I'll quick run up.
Yeah, I can hear you.
Some time ago, using 2 dB, 2.5 dB per kilometer on a fiber, and I suggest to swap the fiber, and somebody said, oh, it's better put another EDFA. Do you think it's a good idea to put an EDFA or change the fiber if you lose 2 dB per kilometer?
That sounds like a terrible fiber. I would look for a...
It took me 7.5 years to change the fiber.
It would be probably...
Management didn't like that.
Yeah, it would probably be more efficient to do an overlay and put it than to the expense of having to put maybe an EDFA or even have to regenerate it, because that's shocking.
I have an answer now, because I was wondering all the year if I was wrong.
No, you're right.
With a zero peak water fiber, would you be able to launch a higher signal than the 16 dB?
Well, obviously you're going to get the best Raman performance using the zero or the low water peak fibers, because I've got the lowest attenuation in the 1430 window.
But can you go higher than the 16 dB maximum launch?
I think there's a...
Or still that's the...
You mean actual total launch power?
Yeah.
I mean, there is probably a limit on the launch power we can go, just because you enter other non-linear impairments if we go too high.
Yeah. The systems you're talking about, the data services, have you done any work in a cable TV network where the performance figures you're typically looking for 40 dB and 6 CNRs at the end of line? And can we use Raman to extend the link budgets in those circumstances?
Are they using, I mean, I suppose it depends on the length. You know, I think what we've been talking about today is a lot of the core networks and maybe some of the shorter haul networks.
80 plus kilometres, 80 to 100 kilometres, typically around 1 or 2 EDFAs in those link budgets.
Absolutely.
Connector losses. Throughout the cable TV industry, we've always used angle polish connectors for years because of the reflections issue.
Yes, as with cable TV, it's always been a...
If somebody said to me, I've got a 1 dB connector loss in a network, I'd be shooting them,
Yeah.
quite frankly.
Well, I mean, by taking out, if you had 2 EDFAs and you had 1 EDFA and a Raman complementing an EDFA, then you're going to get a lower noise figure. So your OSNR is going to increase.
So have you done any experiments or tested one in a cable TV network?
I haven't. I would have to check with the system vendor white papers and see what they've done.
You show the Raman pump really as a preamplifier to the EDFA. Is there any merit in actually moving that Raman amplifier mid-span, for instance, or does it need to be at the end?
Well, I suppose I've just focused on just having it at the end as a pre-complement. You can have just an all-Raman system. But the problem is, if you want to put that Raman, I suppose it's where you've got equipment, where you've got power. So
I was just thinking, if you've got a dozen connectors, you know, moving the Raman amplifier outside.
yeah, I suppose if it was near enough, that's not a bad thing, yes. But I mean, there are some amplifiers that you can have mid-span that you remotely pump.
It's a question about designing a link. Obviously, you've got so many dBs of gain to make up as a combination of the Raman and the EDFA. How much flexibility have you got in assigning the dBs to each type of amplification? I guess the Raman is much harder to control. Is that right?
Well, with the EDFA, I suppose when the system vendor does their design rule, they typically use the same EDFA regardless of your span. And your network might be a 40-kilometre span, followed by an 80, followed by a 50. What they'll probably do is they'll use the same EDFA and actually then just put an attenuator in so they all give about the right amount of gain for each span. So they usually have a maximum gain, but then they can attenuate it down to give you the gain that you want just for that span. The Ramans, it's all driven by your pump power. The bigger the pump power, the bigger the gain.
Any more? Okay, we'll say thank you. Again, please.
Thank you.
Appreciation.